Today I'm going to talk about CUDA and C++. It is important to segregate or to separate into different files those portions of the program that contain the extended C++ syntax required by CUDA, while the rest of the code, those that are pure C++, be in its own separate file as well. And this explains why we have these two files here. So the app.cpp contain parts of the code that will compile in standard C++, whereas those that have extension CU are C++ blocks of code, but it contains extension, certain lines that are no longer valid C++. This is important. We can combine everything into one CU file, both the pure C++ and those that have extended C++. But it is important to separate these two for purposes of organizing your code in the event that your implementation may not have CUDA, or the system under which your code is built does not have CUDA. You can always replace your implementation with non-CUDA alternatives. And if you separate the main logic of your code in a pure C++ file, then you can see it's better this way. So the compiler that is needed to compile the .cu extensions is provided by NVIDIA through this NVCC compiler here. Then it will produce an output file in the form of an object file. Our main app in app.cpp is compiled using standard known C++ compiler in the usual way that every C++ program is compiled. But the CUDA part of the code, which is now an object file, is introduced in the linking phase of the compilation. Hence, it can bypass the syntax check and therefore have a pure C++ in app.cpp, since this is the only one which is compiled, and the .o is introduced, combined into the final executable during linking. It's already an object file. And this is the best way to work with CUDA programming. Let us check the app.cpp first. So we have an include standard CUDA header file here. We even have CUDA data structures such as dem3. We can see also CUDA malloc. So these are CUDA APIs, but since this is still valid C++, this can be combined into this can be considered as a pure C++ parts of CUDA. Now you will notice here some external functions like do transpose and do transpose to. And this is where the implementation is into the static library helper.a in a separate file, which is added here during the linking part. So the test1 and the test2 are just the same attempt to call into the CUDA, but in slightly different way. You can see here that in test 2, there are no references of CUDA traces here. So everything goes into the window gate of do transpose 2, and everything under here is wrapped in CUDA. Whereas in the test 1, you can still see fragments of CUDA constructs, such as dem3, such as CUDA malloc, CUDA memcopy, and so on. So that is just the main difference of test 1 and test 2 to show comparative benefits of pros and cons, which is it's up still to us, it's to the developer which one to choose here. Should we adopt a pure C++ or not? But the point is moot here because these are pure C++ anyway. Now the implementation of do transpose and do transpose 2 is now inside the static library. We will check that next. So this is the implementation of do transpose. And this is the implementation of do transpose 2. So in the do transpose 2, where the client caller is not even using any CUDA data structures, such as CUDA malloc. So this function is doing everything that inside here. And the caller is just passing the float, and all of the CUDA operations are done here. Whereas the other one, the do transpose, only invokes the last portion of CUDA kernel in call here in the transpose, and passing it the parallelized configuration as well as the parameters function. The CUDA kernel, therefore, is this block here. This is where you express the parallel compute block. You will notice most strikingly this triple bracelet opening and closing. This is the most noticeable portions that is not C and C++. The second thing that you will notice here that is alien to C and C++ is this global variable block IDX, block dim, and thread DIDX. These are alien variables that are introduced and whose actual presence is now belongs to the realm of CUDA. So this is not accepted in C++. So let us try to investigate this statement that this is not accepted in C++. Let me create a symlink. So now we have a helper.cpp. So it's important that I have to change the extension. Let me compile this in CPP using a C++ compiler. It is looking for the CUDA runtime. We can solve this by adding the include pass here. So it should be able to find the header file now. So it's complaining for UIInt. This is just an unsigned int. We can mitigate that. So let me put a preprocessor here. So let's give it everything it wants to make it C++ until we reach to a point where it breaks. So now it's looking for the magic variable. Let's try to add the linker library. So this would be to find where the location of the library, the L, and the actual CUDA runtime itself, CUDA RT. and it still could not find this freaking alien variable. Okay, no problem. How about let's continue on. How about let's comment everything here so those alien variable are out of sight. Then let's compile again. And here we are, guys. We reached at the ultimate bottom line of this whole shebang. The triple bracelet is not acceptable in C++. You'll say, yeah, I can invent something like that using C++ template. But remember that CUDA is a C-based API, not C++. It also supports C, and that is where the rubber meets the road. Can no longer help that. That is already a semantic divide, syntax divide between CUDA and standard C++. Right, let's return it back to its formal state. I will remove the C++ and I will put the file back. Now you will see and you will notice the dog here, class dog, an instance of the dog. So the question that I was trying to ask here is, since the CUDA compiler is NVCC, so the question here is it C or is it C++? And that question does not have a simple answer. You have to prove it, not opinionated answer. Is it C or is it C++? Let's try. Let's activate the class, and should it break, then we can conclude that it's only C and so on. I will let the dogs out and then add the dog here, and then so that it will be actually used, I will add it here. Since it's 0, it has a not null effect. So now that we let the dog out, let's compile this. Let us just compile this one CUDA file through this target, helper.co. From this target, we can see that we are dealing one-on-one with this compiler NVCC alone. Make helper.o. Success. And we have helper.o. So you will say, yes, indeed, NVCC is C++, but not quite there yet. We can modify the compiler to pass additional parameters such as the ccbin. Here, the ccbin is the connection between the CUDA compiler and the host compiler. So yes, in the absence of the ccbin, we saw it is C++. But how about if we force it to be GCC? Can it still allow the dogs out? Let us try. And indeed, the dogs are still out. We have generated helper.o. But I'm not yet satisfied here. I would really like to see which host compiler is invoked in all of these adjustments. I will use Linux inotify to watch which compiler is being accessed through this command. Via inotify wait, it will tell me if the GCC is invoked or is it the G++ based on the changes of the code in the makefile above. Let us begin. Right now, with the dogs out and with ccbin marked as specified as GCC, which host compiler is invoked? Let us test. Indeed, the host compiler that is invoked is GCC, despite the dogs are out as a class. So this proves that NVCC alone is, by its very nature, C++ beast. Let's try one more test. If we remove the GCC ccbin here, and if we remove the dog, we put the dog back to the cage. No trace of C++ constructs here anymore. Let's do the test. Okay, it invoked the GCC host compiler. Let's put back the ccbin. And it invoked the G++ compiler. So now we have seen the pattern here that the ccbin indeed does invoke the host compiler by will. We can invoke it by will, but the NVCC on itself is a C++ beast. Why? Let's repeat. Even if we force this to GCC, yet if we let the dogs out, it still compiles. And this proves the point. It invoked the GCC host compiler, yet NVCC allowed with the lets the dogs out condition. That clarifies that part now. So let me discuss this compute capability 5.3 for a little while. So if you have a mismatch of this value, then your code will not run. This is a well-documented versioning, and I am using here a Jetson Nano, and I knew this is 5.3, so I have to put it there. So the compute capability version is some sort of meta information that can tell you what is under the GPU, CUDA, what are the parallel peripherals that is there, does it have an AI or does it have a DNN, stuff. I don't understand them anymore, but that is the principle there. That versioning is important. So let me go back again to app, make sure that I didn't forget something. And that's it. So let's try to run the app. Well, it just transposes a matrix in two ways, and both ways are correctly transposed. It just prints the first three elements of the original matrix and the first three elements of the transpose matrix. So that's why the outputs are just minimal. And again, I'd like to point you to YouTube to understand the principles here. This is parallel programming. You can read that from the books, you can watch that from the YouTube. But what I'm telling you here right now on the investigations that we're doing here, you can only hear it from me, okay? From me only. And I will not repeat the other tutorials about CUDA and its massive parallel programming capabilities. You can watch that in YouTube. My channel will only focus on the things that are not very clear, and I am here to clarify these matters.